the assumptions that we really start from is that you have a classical program, maybe, you know, it's modernizing, it's optimizing, and you want to implement genomic selection in a step-by-step fashion. So we'll try to be very practical. You probably are, you know, already maybe 1 or 2 steps beyond, and that's okay. You can actually put yourself as we move into the different topics. You can see, okay, I'm here actually not at this previous step, etc. But we're going to look at the basics that you need to have in your program to enable genomic selection. And also we're going to try to start with the low-hanging fruits. So try to don't let the fancy stuff dazzle you, as Sanjay was mentioning with some of the literature. So which components to address step by step in the classical program? So this is what we're going to check throughout the presentation. Like I said, we're going to focus on the low-hanging fruits first, and we're going to try to link everything to the breeder's equation. So what questions really, you know, is the one that we are trying to answer today? I think it's only one, but, you know, there is going to be many things coming out from this question. It sounds simple, but it requires many sessions. How to implement genomic prediction strategies in a running breeding program. So let's go through the concepts, and then we're going to try to become more and more pragmatic with the purpose that you can really exploit all the genetic information that you can generate in your breeding program. So, you know, some of the foundations for a successful implementation of genomic selection. Let's start here. We will not go, you know, into the high level of detail, because we assume that these are prerequisites that we will, you know, still spend some considerable time talking about it. But I will try, you know, just to summarize it in general and go over in a couple of slides. But something that we are expecting that, you know, you kind of already are working in your breeding program to optimize is that you have adequate population sizes and powerful field designs. You know, good experimental designs that allow you the creation of what is called a training population in genomic prediction that we will explain later on. So that's something that is really important, having good experimental designs, good population sizes, that you have adopted selection indices that allow you to recycle parents, that probably you are already working on an early testing program, you know, try to produce the trait phenotypes as soon as possible or as fast as possible for the training population. And also something that is normally skipped, that is very important for genomic selection to be a success, is that you are trying to have a closed system that really separates the introgression from the forward breeding pipeline. And that tries basically to introduce diversity kind of in a surgical fashion. So we're gonna actually go step by step for each one of these steps. But you know, a lot of these things are actually not part of genomic prediction. A lot of these things that I'm mentioning are things that you are working in your classical program. You should be trying to optimize, you know, number of families, number of progeny per cross, number of parents. You should be adopting a selection index. You should be trying to go as fast as possible. You should try to generate the phenotypes as soon as possible with high accuracy, etc. So it's not like genomic selection is going to solve all our problems. Actually, we start from the assumption that you are trying to optimize your program, and then genomic prediction is what is going to make it even better. So my general advice to you is that before you actually try to implement genomic selection in your program, you need to make an effort to optimize your conventional phenotypic program and see, you know, kind of genomic selection as a further improvement, as part of an optimization process, not separated. It's just the next step. So the image that I'm showing you here is just a graphical description of, let's say, a typical breeding scheme, you know, that is trying to optimize their crossing strategy. For example, balancing the pedigrees that they use, so they are not consuming the genetic variants that much, that they are actually using only elite parents and not that many, you know, maybe 20, 25 in your crossing block, that has optimized field trials to have the right intensity in terms of individuals, but also in terms of environments. That is basically finding that sweet spot between having many individuals, but also covering the TP as much as possible. On top of that, maybe let me just put my my pointer. So that has optimized the field trials. That's what I was mentioning. And on top of that, uses the best possible surrogates of genetic or breeding value for the different traits. And that has worked to reduce the generation interval by, faster multiplication methods, or like I said, by earlier testing. And as mentioned, that is using a selection index to recycle parents. Basically, if you are not trying to, to improve your conventional phenotypic program, adopting some of these steps, I would say go to that step first before you try to implement genomic prediction, and we will see why is that. When we look at the breeder's equation, and please ignore this part, this shouldn't look like that. So when we look at the breeder's equation, we say that we are trying to optimize the breeding scheme. What we really mean is that for selection intensity, we are trying to lower the cost with same or higher testing capacity. When we talk about the accuracy, we basically are trying to obtain more information, more accurate information, and do better selection. For the genetic variance, we're translating, or we want to translate that genetic variance in genetic gain. It's not about keeping the variance necessarily. I mean, we want to translate that genetic variance into genetic gain. And for the time, when we say we want to optimize, basically we want to reduce the generation interval. Everything just for the sake of having higher response to selection or higher genetic gain. So like I said, we're just starting from some basic ideas. So what can you really expect from genomic prediction? Genomic prediction can really revolutionize the selection if you apply it correctly. But if you actually apply without a clear strategy, it's just going to actually put more cost on your program. You're gonna spend more time, you put more efforts, and actually the benefit is going to be marginal or nothing. That's why you really need to have a clear strategy, have your SOPs, have everything ready, so you can actually extract the juice from it. Despite actually what many people, and even the papers mention, genomic prediction doesn't replace the breeder at all. Actually, if the program first modernizes and is applying the things that I was referring, like selection indices, good surrogates of genetic merit, better experimental designs, then when you get to the inclusion of genomic prediction, almost nothing actually changes in the activities of the breeder. Like I said, in a modern optimized breeding program, really the only thing that would change for the breeder is the time when they are making the decisions. Some of the decisions will happen earlier or later, etc. But really, genomic prediction shouldn't change that much. As you can see, what I'm putting there in the slide, is only one piece of the puzzle, but it's definitely a powerful one once you have the clearest and good strategy to apply it. So as I was mentioning, I mean, what you can expect is drastic changes actually in the rate of response to selection or genetic gain. These slides that I'm going to show just for a minute, these are a courtesy from De Jong and Herring. Here, for example, what you can see in this plot on the left is just the trend for what they call the NVI, which is just the total merit index that is used in the Netherlands and Flanders, so in Belgium, for ranking the bulls and also the longevity. You can see what exactly means NVI, includes these traits, so it's an index, and you can see that when the genomic prediction or genomic selection started to be used, then there was a sudden increase in the rate of response to selection, 60% increase. You can also see the figure on the right, the genetic trend for the index that is used in pigs at PIC, the swine division of Genus, a British-based company. They were having this trend, and when they started using genomic selection, the first cycle, when the results were coming out, then they had a 35% increase. Actually, we think that in plants, this can be much higher, and we're gonna see why. But just to kind of let everyone know that this is kind of a big, drastic or game changer in breeding programs. But as I mentioned before, let's not forget that this is just the next step after you are trying to optimize your conventional breeding program. So to introduce the genomic selection, let's just talk for a minute about pedigree blob, a method established a long time ago in animal breeding, really a long time ago, and how this method kind of took us in the thinking of genomic selection, and it helped us to actually to all the breeders around the world to take the next step. And don't worry, this is going to be plant breeding based. I'm just putting some figures to kind of present a historical view. Of course, this is a simplified view. I'm not going to talk about the details of animal breeding, just some key characteristics why pedigree blob have been used for decades. You know, in a regular animal breeding program, you can just use the information from the pedigree, all these covariants that exist due to family relationships to enable prediction. Basically, you can predict across a single or few individuals with as much information, from relatives as possible. So really what you are trying to do is just to borrow information between family members with the purpose, like we said, to predict across, or maybe predict the breeding value for specific traits for individuals that actually cannot present that trait. Let's think, for example, milk in bulls. This is a trait that they cannot actually produce, but you can just predict what would be the milk production for those individuals. So you can make basically selection of individuals with or without information on the actual individual, but thanks to the information that exists in the family members, full sibs, half sibs, cousins in second, first grade, etc. You can come up with a specific value for the different traits. This is particularly important for bulls, like I said, because they will be used in many crosses once they become sires, and they get useful information before these crosses are evaluated. But let's not go too much into how the animal breeding schemes look like. But for many of you, probably you know the way pedigree works. So instead of assuming that observations, like for a long time in plant breeding has been assumed that observations or records on individuals are independent. Instead, because the limited information that the animals breeders generate, instead they started to look at how to use the information from the relatives. So here we assume that individuals having family relationships provide some information to each other, basically that they can borrow information. For example, look at this numerator relationship matrix. So basically this is information from the pedigree converted in what is called a relationship matrix. So same number of rows as same number of columns and rows representing different individuals. It starts, let's say, this pedigree with 3 sires or fathers and 3 mothers or dams. You can see that they actually show up as having no relationship between any of them. Let's say they are the founders, and they gave rise to different families where you can find, let's say, these next individuals, 3, 4, 5 new dams that come up out of those individuals. You can find some that are full sibs. For example, let's look for a 0.5. So dam 8 and dam 4, they are full sibs. There might be some half sibs, the 0.25, and also some cousins in first grade. And then at the end of the matrix, you actually have another 3 individuals. And these individuals highlighted in yellow, basically 2 of them, for example, the 3 of them are full sibs, but the bulls, that you can actually predict the milk production for these individuals, even though they cannot generate that phenotype, but because you have a dam that has, that can produce the phenotype, you can use the information from this dam to predict what is the milk production for bulls. Of course, the big problem with using the pedigree, as you can see here, is that basically you cannot distinguish between the predictions of these 2 full sibs. Basically, the prediction for these 2 individuals, bull 1 and bull 2, it will be exactly the same. You cannot distinguish between basically the Mendelian sampling. So all these prediction methods, as you can notice, are based on genetic covariances using the family relationships, the concepts of identity by descent. Later, of course, we will talk about the identity by state, which basically is traced throughout the ancestral meiosis that goes back to the founders. So I hope that is more or less that you are familiar with it. That's how the pedigree blob actually works. How all this prediction stuff started to take importance in animal breeding, and little by little is basically the basis of genomic prediction. So I hope this animation helps just to put the basics on how genomic prediction works. As some of you know, the information comes in these genomic prediction models from what we call a training population. That is basically a set of individuals that should have certain relationship, or that they belong to a breeding program. And this training or set of individuals aims to predict another set of individuals that we call the validation population, or the prediction population, depending on which context you are. And this is where the foundations or prerequisites that we were referring at the beginning really comes into the scene. Having a closed breeding system really maximizes that relationship between the training set, the one that we have here, the training population, which can be taught as the material that you phenotype at the different stages, basically the material that your program is generating in a normal basis. And if the program is closed, then it's going to be highly related with what you want to predict. But if you have an open system, you are bringing germplasm from all the different places around the world, every crossing block, or you'd like to make your introgression crosses together with your forward breeding material, this training population is very likely that will be a very poor source of a good prediction model. So, but let's assume for a minute that, like I said, that you are optimizing your breeding scheme, you are closing the system, you are adopting selection indices, etc., etc. Once you have the phenotypes and the genotypes for those individuals that we will call the training set, this can be used to feed a model that will contain, that will produce instead, what we call marker effects. So we will be able to assign a value to the different markers for all those materials that you have genotyped. Then you can genotype, let's say, any other individual from any stage, let's say your stage 1 of yield trials, or your stage 2 of yield trials, or your nurseries, etc. You can genotype any individual that you want from any stage in your program and fit a model to basically predict the genetic estimated breeding values or genetic values, depending on if you are working in an inbred or a non-inbred crop. And then you're ready to take any of the two decisions. Either you can select new parents to reduce the cycle time, and just to advance materials into later stages as well in the field trials, just to do it with more accuracy, not necessarily to reduce the cycle time. And that is part of what we call, in the case of the left side, is what we call the population improvement. You're trying to increase the allele frequency of the positive alleles to produce genetic gain. And the one on the right side is the product development component of your program that is trying to produce products faster. So basically the decision of what do you genotype is going to depend on what are you trying to do. Are you trying to make population improvement, or are you trying to do product development? Like I said, in the case of product development, you may want to just genotype something in the advanced trial to move it faster, so you can release the product faster. In the case of population improvement, you may want to actually genotype very early in the pipeline to identify parents as quick as possible. But let's go step by step. So because in the case of genomic prediction, there is a change in paradigm, because now the allele is what becomes the unit of testing, is what becomes the unit that you are replicating, not the individuals anymore. In the classical conventional pipelines, the individual is what you actually are using for selection. And in the case of genomic prediction strategies, well, alleles are massively replicated, not like the individuals that are maybe you only have 1 rep or 2 reps. Even when the number of individuals is low, you know, the allele replication is actually quite high. So you can either use, you know, there is just some minor details, but in general, you can either use the genotype information, just like the genotype matrix, or convert it into a genomic relationship matrix to predict individuals within your breeding program. Really, there is some equivalence in the methods that use either directly the marker matrix or the ones that build a genomic relationship matrix. Of course, as some of you may know, for the ones that don't, this might be, of course, important. If you look at the exact same relationship matrix that we were showing before, but instead of building it with the pedigrees and the expected relationships, like, you know, mother to son of 0.5, or I don't know, half SIFs or you know, full SIFs, in the case full SIFs 0.5 as well, or 0.25 for half SIFs. In the case of marker matrices that are used to build relationship matrices, you can actually distinguish differences between these individuals. In the case of, you know, for example, we're referring last time to the bulls that are full SIFs. In the previous slide, probably you may remember that all this information was exactly the same, and you couldn't distinguish between these 2 bulls. But because now we are using marker information, and in bull 1 and bull 2, they have different genotypes for certain markers, now you are able to actually capture differences between individuals that will allow you to predict the Mendelian sampling. So pedigree and versus, you know, using genomic prediction, they can be actually equal if you are not able to, or you are not trying to take advantage of the Mendelian sampling. For example, for predicting a cross, they will give you very similar results. But for predicting individuals within a cross, genomic prediction is the only one that allows you to distinguish between falsies, basically to predict that Mendelian sampling that it was not possible before. So, you know, for these individuals that we were calling training population, or also for the individuals that you want to predict, the predicted population, basically you have to generate a genotype matrix. So in the case of this matrix, it's just a Mickey Mouse example, but here in rows, you can see, let's say, the IDs for the individuals, genotype 1, genotype 2, or let's call it material 1, material 2, 3, 4. Of course, there can be as many as you want. And you, in columns, you can see basically the name of the markers, SNP 1, 2, 3, 4, 5, 10,000, etc., etc. And the numbers that you see here is just the numbers that tells you what is the frequency of a given allele. So you randomly normally take, let's say, if you decide, let's say that is a SNP and it's either one letter or the other, you take any of the letters and you say how many of those letters exist. And so basically you say there is 0, 1, or 2 of those for a diploid. For a tetraploid, you say if there is 0, 1, 2, 3, or 4. So basically you put the dosage of for that given marker. And normally you center those matrices, and that's why you see this as -1, 0, 1 in some of the values. Is just taking the 0, 1, 2 and you know, subtracting a 1. And also for the case of the polyploid crops, you also have to center those matrices. But you can always take those matrices and just convert them in relationship matrices by just taking the cross product of those two, of this matrix. So it's just like taking this times its transpose to generate a matrix that is just the dimensions for the genotype. So it's a 4x4. Here, for example, was a 4x5. If you take the cross product of this matrix, you end up, you know, with 4 rows, but also with 4 columns, and that's how you get this one. So you can use any of the two. I mean, it's just a different model, but they should give you the exact same results. Some have their benefits, and some have, you know, also their disadvantages. This is the preferred one because it's computationally less expensive. So basically, before we obtain this relationship matrix, there was a marker matrix. So there was a marker matrix for all these individuals. Maybe there was 10,000 markers, so there was 10,000 columns. But once you make the cross product, you ended up just with a matrix that has the same number of individuals in columns and rows. So let's see what are the major differences between animal and plant breeding that is important to keep in mind, because you have to avoid sometimes trying to apply everything out of animal breeding world as it is, because actually some of those things do not apply to plant breeding. For example, let's take a look at number one. In the case of animal breeding, normally there is single or few individuals per cross. When you make a cross between a bull and a dam, or a sire and a dam, it's not that you can generate, I don't know, 1,000 progeny or 100 progeny or something like that. It's not the case in animals. That is something very different, of course, in plants, at least in most of them, where you can generate many individuals per cross. That means that if you have a relatively closed system, like the one that I was mentioning that we are trying to aim, you actually don't need those training populations of hundreds of thousands or millions of records that the animal breeders actually try to build, because they are trying to build from the numbers, because they cannot build strong relationships. They need to rely on few full sieves, a couple of half sieves, some cousins, etc., etc. That's why they actually have in their training populations even sometimes millions of records to achieve kind of the same prediction accuracies that the plant breeders can achieve, because plant breeders have the advantage that they can generate relatively big families. Another thing that is quite different and is important is that sometimes in the case of animals, they cannot generate information in the progeny, like we said in the case of bulls, they cannot generate milk records, but also there is very limited information because progeny is limited. Whereas in the case of plant breeders, I mean, their crops, they normally can generate information in all descendants. At least traits are normally measurable in all individuals in plant breeding, as opposed to sex-specific traits. Even in plants where you have, a specific sex or sexes, still most of the traits you can still sometimes generate the phenotypes. In addition, phenotyping is cheaper in plant breeding compared to animal breeding, because you have to basically grow this animal for many years to generate a couple of records or several records. But in the case of plant breeding, normally the generation intervals are also shorter. Sometimes it can be extremely long as well for some of the plants. Let me think, for example, in the forestry, also some of the fruit crops, they also can be quite long. Let's think on banana or sometimes even avocados, something like that. But in general, most of the crops actually have shorter generation intervals than several animals. But just, in general, there is always small differences.